monitoring Church Lake for just over a year now. Now, Church Lake is a residential lake over in eastern Grand Rapids off of the East Beltline, which is a major road that goes to that area. And it is currently experiencing high salinity issues due to road salt runoff. And well, the issue with high salinity in lakes, there's honestly a lot, but the main one that we were looking at was the prevention of seasonal lake turnover, which can cause just a number of different issues in lake structure and with aquatic life. What's really interesting about this area, though, is that the tributary here that flows from underneath the East Beltline into Church Lake actually has high conductivity and high chloride concentrations throughout the year, including in the summer when there is no road salt being applied. So the objectives mainly with my project was to analyze the retention and release of chloride within these tributary and floodplain sediments to see if this could possibly be the source of chloride during the summer. And I also analyzed the effect of chloride on the retention and release of other nutrients and ions, mainly SRP, sodium, and calcium. So first off, looking at project design, we decided pretty early on that I was going to be doing 2 flow-through experiments, one with salinized tributary water, where I brought the chloride levels up to what was seen earlier that year in the spring, and the other with DI water. And this was really to replicate those conditions of that first spring runoff event and then a summer rain event to see what was really going on between those 2 events. And I also conducted these experiments in environmental growth chambers to have it at 8 degrees Celsius for the first experiment and 24 degrees for the second, again, to really replicate those field conditions. Now, when it comes to dispersing the water, I decided to build gravity-fed drip systems for this. And as you can kind of see here, there was a bucket up above that then fed water down to the drip valves connected to this PVC grid. And they were each calibrated to about 200 milliliters per hour. And then they were inserted into the cores that were hung from that PVC grid. And then water was allowed to drip into the tubes for about 3 hours per experiment. And then the water percolated through the sediments and the effluent was collected out the bottom here. So looking at coring, I decided to split the tributary up into 3 cross sections. The first was up by the East Beltline. The second was more in the midstream location. And the third was at the mouth into Church Lake. And there were 3 sites per cross section, one in the middle of the tributary, and then one on each of the floodplains. And I also did a triplicate analysis, so there were 3 cores per site for a total of 27 overall. So going into my data analysis, first off, Ellen actually found a very, very strong correlation between chloride and conductivity in the tributary, so much so it was actually a 0.92 R squared, which is just ridiculously high for any kind of field data like that. So I actually ended up using conductivity and then converting it over into chloride concentrations for my data. And these are the chloride concentrations for the first experiment. I conducted paired t-tests between the before and after to try to find that significant difference. So this is actually the difference in chloride concentration from the salinized tributary water. And as you can see here, while there were some cores that actually seemed like they released a very small amount of chloride, most of them actually retained some of it because there was a significant difference between the tributary water and the effluent, and that there was a decrease. And also, just to give you a bit of an idea of just how high these were, so I elevated the chloride concentration in the tributary water to 548 milligrams per liter. The mean effluent value was 524. Now, the EGLE has an aquatic maximum value where it can start to harm aquatic life. This was 320. And that's actually pretty generous because a lot of them, like the EPA, say that it actually should be more like 250. So these were just ridiculously high levels in this tributary. Now, this is the distribution of chloride as you move down the tributary. So I did a NOVA test to see if there was a significant difference between the cross sections, to see if maybe more or less was retained as you move down the tributary. You can actually see here these box plots, each one represents one of the cross sections here. They actually were very consistent in this first experiment, and there really wasn't any kind of significant difference as you move down the tributary. So for the second experiment, you can see that there was definitely a shift here. So instead of having retention, there was actually a huge release. And the values got up pretty high here. It was a little bit more, there wasn't as much like a normal curve here, definitely a little bit more skewed. And just to give you an idea, so again, it does make sense that there was a release in this second experiment because the inflow concentration was 0 milligrams per liter because it was DI water. But you had this increase of 105 milligrams per liter on average. And while this is much lower than the aquatic maximum value, you also have to remember that this is possibly in addition to what would already be naturally in the water. So again, looking at the chloride distributions, there was definitely not as much like consistency between the cross sections, but there was not a significant difference between any of them. Now, how to interpret this data? In all honesty, a lot of this is very much preliminary. We've never really done this kind of test in the lab before, and there also isn't a whole lot of literature out there either. So it's hard to, I don't want to draw too many conclusions from this because there's just so much unknown. But at the same time, it does look like there was a significant retention of chloride in the first experiment and then a significant release in the second. And again, there isn't really much understood about how this happens. So the processes within sediment is also unknown in this sense. But I am also conducting organic matter analysis currently, and I'm hoping that using that to normalize the chloride concentration in some of my other data will help clarify things, maybe even produce some significant differences between the cross sections. And also, I mentioned before that I was looking at SRP, calcium, and sodium. I only just recently got some of that back, so I'm still analyzing it. I also just couldn't fit it in here. It's just too much, but it is very interesting. So if you'd like to talk to me about it later, please do. I think it's very cool. So that's all I have. As far as acknowledgements, first off, I have to thank Al, of course, for hiring me in the first place and giving me the opportunity to do this and developing this project with me. I learned so much, and I've just had so much fun with it. And Maggie is no longer here, but she did deal with a lot of my questions before she left, so I kind of had to put her up here. And Mike, of course, I have to thank. He not only answered a lot of my questions, but he was also out in the field with me, even did some coring, and there was poison ivy everywhere, so thank you for dealing with that. And Taylor, my fellow intern, we had a lot of fun coming up with my project design. Definitely a couple stories there, so that was fun. And Paris is also not here right now, but she, again, just like with Taylor's project, she took a lot of the pictures, helped me carry stuff, which is great. Brian, thank you for being patient enough to have me with testing the SRP. I appreciate it. That was great. And of course, I have to thank Ellen for collaborating with me on this and just being a great person to be out in the field with. Thank you to all of you. It was a really, really great experience. I had a lot of fun. And thank you to all of you for listening. And are there any questions?
Questions for Jacquie? What was your favorite part of the project?
There was a lot. It was really cool. I guess one of the biggest parts was, getting this whole thing set up was a process, which you will remember. It was, a long field day, and then also getting the drip systems built it was like easily a month of prep work, to be honest. But then, getting back that data and seeing that they're actually what I'd read about in these papers that I'd gone over, and then seeing that was actually happening in these cores was just, that's always really rewarding, and the whole data analysis process was just really fun for me.
I want to point out Jackie's impression, so it's really incredible what you've done. It's like your career.
I have a tough question. What do you think is driving the main difference between retention and reuse? Because you had chloride differences between your two treatments and temperature differences. So do you think one is driving it more than the other, or do you think they're just working synergistically? Or
I think that with pointing out with the temperature, I think that could be something I look more into in the future, seeing if that does actually produce a difference. I believe most of it is just the chloride concentrations. The second experiment, you didn't have any. I was really just trying to see how much can I actually get to come out of these cores in that second experiment. What's interesting with the first one is that there wasn't actually as much retention in the sediment as I thought there would be. But I think that possibly could be that I just accidentally found the limit of how much chloride could actually be retained in these sediments. So one of the things that we could do in the future is doing an isotherms test to see if I could find that value where it stops being retained and instead is being released.
any further questions? Great.